Okay, let's continue with 601 and find the area under and between curves. Let's do another example. Find the area of the region bounded by the curves, the inverse cosine of x over 3, y equals 0, and x equals 1, obtained by integrating with respect to y. Okay, so it's usually best to start with a picture. So let's graph these. We have the inverse cosine here in the red curve, x equals 1, and y equals 0 is the x-axis. Okay, so the area that's bounded by those, x-axis, red graph, purple graph, is this area here. And we are going to be integrating with respect to y, which means we're going to talk horizontal lines here. When we want to find the distance between something, like if you remember in chapter 5, if you have a graph from here to here, let's say we want to find the area underneath this graph. Well, we learned that if you integrate, like let's just pretend that this is y equals x squared, total sidebar right now, and this is at x equals 1. So if we integrate from 0 to 1 of x squared, well, that is a y. This represents y, and y is measured vertically. So when you put something with x's right here, that means that we're talking a y value. We're talking a vertical line because the point is on the graph and this point right here is measured vertically. It's a distance. And the distance of this point that I just drew, random one, because there's infinite number of points here, is a y value. It tells you the distance vertically. So that's why when you integrate something with x's here, you're actually finding distance vertically. And you're integrating with respect to x, but you're using the y-axis to measure. So this gives us the height. Remember, these are just rectangles. So the height of that rectangle is technically the y-coordinate of the graph right here. So that's what happens when you integrate with respect to x. When we integrate with respect to y, we're talking horizontal. So now it's a new formula. It's the right curve minus the left curve. Instead of it being the top minus the bottom, it's right minus left. And here's why. This is the distance. And again, this is random. There are infinite number of these. I know these are not very straight. But these are all little rectangles, just like you learned in chapter 5. And then this is how you find the area from the y-axis to this graph, because that represents the inverse cosine graph. Now, that horizontal distance is not measured by the y-axis. It's actually measured by the x-axis. This point right here, the x-coordinate would tell me how long that line is. It's a distance. It's somewhere between 2 and 3, closer to 3, just that point specifically. But all of these points, if I wanted to know the length of the horizontal line that connects it to the y-axis, it would be an x value. It would be the distance on the x-axis. So this is going to have to be solved for x. And the same thing for x equals 1. This is actually already solved for x. The distance here is constantly going to be x equals 1. And we're going to have to stop right there because that's the end of our boundary. So when we want to do the area of the right curve minus the left curve, we find the area of the right curve, which is this whole distance, and then we subtract it from the area of the left curve, which is this green piece. And if you take that orange piece minus the green piece, you're going to be left with just this area here. And if you imagine an infinite number of those situations creating this, you'll end up with just this area here. So when you're integrating with respect to y, we're going to need to solve for x because this distance represents some x coordinate. It's a distance, remember. And then you need to remember to do the right curve minus the left curve. So let's take this equation and we need to solve it for x. So now what we're looking at, when we have it set equal to y like this, it gives us a y value. To solve it for x, we need to undo what's happening to the x, which in this case, it's the inverse cosine. So if you want to undo the inverse cosine, you do the inverse of the inverse cosine, which is just cosine to both sides. Like we just took cosine to both sides, just like you would square root or square both sides to undo something like that. And now we can multiply by 3. And now that represents the x-coordinate. Every single one of these points is an x-coordinate now. X equals, it'll tell us what the point is on this graph. Okay, we needed that. That's going to be the right part. And then the left part is already solved for x. It's x equals 1. So our integral is going to be, this is the right curve, and then this is the left curve. X equals 3 cosine y minus x equals 1. And notice we have dy. And the dy, if you're a little confused on this, if you integrate with respect to y, you're going to have a y here, which means that you should have y's as your variables in here. And if you have a y in here, it means you had to solve for x. You have x equals. And it's all because the measuring is horizontal now. Okay, so our bounded region is this section here. And because we're integrating with respect to y, we need to measure it along the y-axis. Those aren't zeros, those are just fill in the blanks. So we're starting at 0, but the last one is going to be right around here. So before we can do our limits, we need to set these equal to each other. So you can graph them. This is probably easiest to do in your calculator. And then find the point of intersection. Or you can set them equal to each other. Remember, if they're both solved for x equals this and x equals this, you can set them equal to each other and solve for y here. We need to know the y coordinate, so it'll tell us. You would just have to divide by 3 and then undo the cosine with the inverse. And you can stick this in your calculator. Either way, you need your calculator because this is not a pretty number. So you can either graph these two equations, and you could graph it like this because we can't graph in x equals form. You'd have to graph it like this. And now that I think about it, you can't put this in a calculator. You'd have to do this online or just find the points when x equals 1. Oh, hey, I'm making this really complicated, aren't I? Just plug in 1 right there for x. Love it. Anyway, so use your calculator. You get 1.23 here is your y coordinate up here. And then just integrate from there. You're going to need a calculator for this, but integrate the integral of cosine will be sine. The integral of 1 is y. And then from 0 to 1.23, use the fundamental theorem, plug numbers in, and then simplify. Okay, so I assume you have to pause this and do it yourself so you can check to make sure you get it right. Don't just look at me and make sure I did it right. Sometimes I make mistakes and I don't catch them. Okay, next one. Write the integral used to represent the area in the first quadrant bounded by the graphs of y squared equals x minus 4, x equals 1, y equals 2 by integrating with respect to x. Okay, let's draw a picture. Always the best thing in this chapter or these types of problems, and 602 as well, you're going to want to draw pictures and look at what you're dealing with. Okay, so y squared is really, if we can't graph a y squared in your calculator, so if you square root both sides, and remember when you square root, you always have a plus and a minus. So the top half of x, the square root of x minus 4 is here, that's the positive one, and then the bottom half is this negative one here. But we're only working in the first quadrant, so we really don't need to deal with this one. And we're bounded by x equals 1, which is right here, and y equals 2. So first quadrant, x equals 1, y equals 2, and we've got this situation going. So this is our area section that we're trying to, we only have to write the integral, we don't have to find the area this time. Okay, when we integrate with respect to x, that means we're talking vertical lines because it's going to give us y coordinates. Like I said in that last example, I drew a picture of x, this is y equals x squared from 0 to 1. So when you do that, it finds the area under the curve vertically. So anytime you integrate with respect to x, you're dealing vertically because it's going to give us the distance on the y-axis. So notice that the distance here from 1 to this point is the same. From 1 to 4, the distance under the curve is 2 for every single little rectangle that would be drawn, every single one of them. It's actually just a rectangle right there. From 0 to 4, we have a rectangle. So don't make that any harder than it has to be, but we still have to write this as an integral. So we're not finding the area this time. We're actually just writing it out, as an integral. So pretend that this other half doesn't exist for a second. We're not even dealing with this. Ignore this. And we're just finding the area from 1 to 4 of y equals 2. The area of 1 to 4 of y equals 2. And we're doing things with respect to x. So that means that we're dealing with vertical distance, and that vertical distance is a 2 for every point between 1 and 4. So that would represent that first chunk from 1 to 4. Let's make this look a little neater. There we go. I'm scribbling all over the place. So that's it. If you have a rectangle, it's just the y coordinate from the lower to the upper limit. So in this case, it's 1 to 4, y equals 2 because the distance is the same. It's going to be a measurement of 2, a vertical measurement. Okay, so now let's talk about this section because now we have to find the area of this piece here. And now this piece, there is, going to be a situation where we have to find top curve minus bottom curve. Again, if you find the area, or I'm sorry, if you find the distance from here to here, which is going to be 2 again, all the way from 4 to 8, because that's the point of intersection here. And then if you subtract this distance, it's going to give us this little piece right here. So that's why we do top curve minus bottom curve, because we take, it's all distance. We're taking this line and we're taking away this line from it. So it'll just leave us with the smaller piece. So that section is going to be 2, which is the top curve. Y equals 2 is the top curve. And this bottom curve is y equals the square root of x minus 4. And that happens from 4 to 8. So each one of those, we had to separate this because the bottom curve wasn't the same. The bottom curve here did not start until 4. So final answer, we had to take this and split it up into 2 pieces because from 1 to 4, the bottom curve was technically y equals 0. So if you wanted to, we could have done top curve minus bottom curve here, where the top curve is y equals 2 and the bottom curve is y equals 0. That's fine. This would just look like 2 minus 0, which you don't really need a 0 there. And then starting at 4, the top curve is still y minus 2, or I'm sorry, y equals 2, but the bottom curve is y equals the square root of x minus 4. So that happened from 4 to 8. Okay, hopefully that makes a little sense.